Laser pulses bounced off Apollo mirrors show the moon is drifting away, 3.8 centimeters each year. How can gravity make an orbit expand? Those Apollo mirrors are retroreflectors. They send light straight back to the source. The round trip takes about 2.5 seconds, so we can measure the Earth-Moon distance, about 300 to 400 kilometers, to within millimeters. And the distance keeps increasing year after year. That's weird because gravity only attracts. In an orbit, gravity is the inward bend that keeps a sideways moving object from flying off. If the moon lost speed, it would spiral inward. Yet the measurements say the opposite. The orbit is slowly widening. Does moving outward mean the moon is getting faster? Counterintuitively, higher orbits are slower. The moon circles Earth at about 1 kilometer per second. The much closer space station races around 7.7 kilometers per second. Farther out, you can move more slowly and still not fall. So, why does drifting outward still require energy? Because orbital energy isn't just speed. It's also height in a gravitational field. Throw a ball upward. It slows down, but you had to pay energy to lift it. Gravity by itself can't pay that bill. Over an orbit, it gives back what it takes. Step back. The moon is gaining orbital energy, so something else in the system must be losing energy. So, what internal engine pays that bill? Earth's rotation, coupled to the moon by tides. A tidal force is gravity's gradient. The near side of Earth is pulled a bit more than the far side, so Earth stretches. That stretch makes 2 bulges, mostly in the oceans, but also in solid rock. Earth spins once every 24 hours. The moon orbits in 27.3 days. Because the planet spins so much faster, it tries to drag the bulges ahead of the moon. Real oceans don't slide freely. Water rubs on sea floors and funnels through coastlines, so the bulge can't instantly snap back into line. It stays a few degrees in front. Now, watch the forces. The moon pulls on that forward bulge, and the bulge pulls on the moon. Because the bulge is ahead, part of the pull points along the moon's path, giving it a tiny forward kick. That increases the moon's orbital angular momentum, its spin-around Earth budget, so the orbit widens. The reaction is equal and opposite. The moon's pull creates a torque, a twist that slows Earth's rotation. No fuel burned, no thrust, just gravity, plus friction dumping a few terawatts of tidal motion into heat. Stepping back, the moon moves outward because Earth is literally braking. How small is that effect on a human timescale? The moon retreats 3.8 centimeters per year, about the width of your thumbnail. But that's 38 kilometers in a million years, and the direction has been the same for most of Earth's history. We can see the payment on Earth. The day lengthens by about 1.7 milliseconds per century, measured with atomic clocks and even hinted at in ancient eclipse timings. That lost spin shows up as a wider lunar orbit. The month lengthens by a fraction of a millisecond per year, and the sign can flip. If Earth ever rotated slower than the moon orbits, the tidal bulge would trail behind, and gravity would tug the moon backward, shrinking the orbit instead of growing it. Mars's moon Phobos is doing exactly that, spiraling inward by a couple of centimeters per year. Stepping back, tides are a machine for transferring angular momentum between spin and orbit, and the lead decides who gains. What does this slow migration change in the long run? Start with eclipses. If you watch the 2024 total eclipse, that perfect fit is temporary. The moon looks about half a degree wide in our sky today, just barely big enough to cover the sun. As it recedes, its apparent size shrinks, and in roughly 600 million years, perfect total eclipses should be gone. Tides weaken even faster because tidal strength drops with the cube of distance. Twice as far means 1/8 the tidal pull. A moon half as far would mean 8 times stronger tides. So in the deep past, when the moon was closer, coastlines were worked harder and Earth's rotation was faster. Some fossils record years with about 400 days, just a few dozen more than today because each day was shorter. Given enough time, the end state is tidal locking. Rotation and orbit synchronize so the same face always points inward. Pluto and Charon have already reached it, circling every 6.4 days. Earth and the moon are heading that way too, though the sun's evolution will likely interfere first. Stepping back, the moon's retreat isn't just trivia, it's a slow resculpting of Earth's environment. Gravity isn't pushing the moon away. Earth's tides trade our spin for the moon's orbit. The ocean's drag turns motion into heat, and gravity turns that drag into a torque that transfers angular momentum outward. Centimeter by centimeter, the moon climbs. Stepping back, those lasers are measuring a planetary scale energy transaction. The next time you watch the tide rise, you're watching Earth very slightly slow down. You're watching the moon very slightly leave. If tides can reshape an orbit for 4.5 billion years, imagine what they do in tightly packed exoplanet systems. Like, if this was interesting, hit the subscribe for more and turn that notification bell on